Right, I've got a worked examples video. This is for proof by induction. So I've got three different types of proofs by induction. So hopefully will prove helpful. Right, okay, so this is the first one. Prove by induction that for all positive integers n, this expression here, the sum from 1 to 2n of r squared equals this thing here. Now you might notice this actually is a sort of adaptation uh, of this formula here, which is the formula for the sum of the squares from 1 to n. And to be honest, I looked at this and I thought, well, can we not just do a substitution? Um, which we may be able to, but I didn't do it that way anyway. So it possibly you might be able to do it more simply with a substitution. But I was still toying with the idea of whether or not it was a valid thing to do. But no matter. Okay, so useful to define f of n, I think, in these situations. So that is the sum of 1 to 2n. So that's just this thing. And therefore, the sum from 1 to n plus 1 is that. Okay, all right, so establish the base case. We'll look at the f of 1, and that turns out to be 5, and if we put that into the right-hand side here, we find that that is equal to 5. So it is true, therefore, for n equals 1. Right, our assumption, our assumptive step, if you like, assume that it's true for n. So in other words, our expression holds. And then the induction looks something like this. Well, so what this is saying is that the additional the additional term as we go from n to n plus 1 in this case is actually two terms here. Okay, because if we're going for 2, n is n plus 1, that's taking us from the sum from r equals 1 to 2n plus 2. So our extra terms are 2n plus 1 and 2n plus 2. Okay. So if we were write it this way around, well, we could write f of n plus 1 minus f of n equals this. Yeah, okay, but just adding f of n to the right hand side, we get this. Well, that is fn there, f of n, that plus that. Right, okay. So now if we uh, factorize out a third, that means we're going to multiply this thing by 3. And what I've done there is I've kind of maybe skipped a step and actually worked that through into this. So the total of this parenthesis is going to be equal to that. And then I've just factorized it now. I've taken n plus 1 because I can see we're going to need n plus 1. We go back to here, then, I'm going to have to prove it for n plus 1. So taking n plus 1 out, leaving that, and then that factorizes to that. And then when I take n plus 1 out of that and that, it leaves me with this. And I've shown this in red. So this basically shows the same expression, but with n plus 1 substituted for n. Now, a lot of these proofs actually do a substitution and use k. Actually, find it rather clearer to to not start using extra letters. So hopefully, you find that clear yourselves. And I think it does satisfy the necessary rigor. But if you wanted to adapt it and do a substitution for k, like some of these examples, then you can do that. So if we compare that to the original expression there, we can see that basically it's the same, but we've got n plus 1 instead of n. So therefore, the conclusion is that it being true for n implies that it's true for n plus 1, and since it's true for n equals 1, then it is true for all n. That's the basic idea. Right, okay, so uh, you can stop and rewind that at any point, of course, as with any of these. Right, this is a slightly different thing. We've got an expression here. We're proving an expression, but this has got a kind of two-step relationship. I know I wasn't even sure what to call this, but we can see this thing that's given here involves kind of um, three different subscripts. You know, u sub n plus 2 equals 5 u sub n plus 1 minus 6 u sub n. All right, so given that that's the case, and we're given those two as well, prove by induction this. Right, so for this we sort of need a double base case. So it's not just good enough to prove for u equals 1. We're applying for u equals 2 and 3 as well at the same time. So if we evaluate these, because that's the only way we can actually, this is what actually proves the base case, is when we evaluate it with these sort of 1, 2s and, you know, sort of minimal values in here. So U3, which perhaps I should have just written in there just to be completely clear, is equal to 5u2 minus 6u1. So obviously we're going to need u3, u2, and u1 in order to be able to do that. Okay, so or at least we're going to need u2 and u1 in order to be able to calculate u3 and verify that in the base case. That's what I'm saying. All right, so well, we do that. We can calculate all those u1 and u2. This line actually doesn't make too much difference, but we can calculate U3 from that. Okay, so we can show the base case as a result of that. Now, assumption is it's true for n. So in other words, that is also true. And therefore, and also it's true for n plus 1. Right, for the same reasons, you know, our given here involves three terms, three different values of n, if you like. Okay, so so the induction therefore is to show un plus 2 is equal to, let me just kind of slow that down so we can see the relationship there. Yeah. So un plus 2 equals 5 times un plus 1, which is this. Okay, so we've basically got 2 to the power of n plus 1 plus 1. Yep, so that's 2 to the power of n plus 2, plus 3 to the power of n plus 1 plus 1, which is that, minus 6 times un, and un is, well, we can read it off here, 2 to the power of n plus 1 plus 3 to the power of n plus 1. Right. Okay. Right, so where's that leave us? So, well, if we sort of group these terms together into this and these into this, then what we've got, well, that's 10 there, isn't it? And there's 6 there, so it's 4 lots of that, 4 lots of 2 to the power of n plus 1. And that's 15, and that's 6, so that's 9 lots of 3 to the power of n plus 1, which we could restate as 2 to the power of n plus 3, 3 to the power of n plus 3. Okay, which we can write as 2 to the power of n plus 2 plus 1 plus 3 to the power of n plus 2 plus 1. Okay, so that equals that. Okay, the n plus 2th term is that, which is exactly what we've got in our assumption. Okay, so since it's true for 1, 2, and 3, and then it's true for n and n plus 1, that's the assumption that we made, then it's true for n plus 2, and therefore it's true for all n. Okay, right. Okay, so that's a slightly more complicated one. I hope that is clear. And then we've got another type here where we're not proving an expression like a sum or anything like that. We're basically proving a property, and this property is that for all n, this expression is divisible by 17. So the property is divisibility by 17. Okay, so that's what we've got. We don't have to define f of n here. It's already done for us. And that is equal to 391, which is equal to 17 times 23. Okay, so therefore it is true for n equals 1. And now we're going to assume that it's true for n. In other words, yeah, this. And the induction is, well, what we're doing here is basically, if we assume that it's true for that, and it's true for the difference of the two, then it must be true for f of n plus 1. Right. Okay, now the difference of these two is, this is f of n plus 1, and this is f of n. Right. So if we rearrange and we collect this term with this term, and we factorize out 2 to the power of 3n plus 1 there, then we've got 2 cubed, which sort of comes from this here. This is 2 cubed times 2 to the power of 3n plus 1. Yeah. Minus 1. And then likewise with these two terms, this one effectively gives us a 5 squared. Yeah, so 3 times 5 squared times 5 to the power of 2n plus 1. So we can factorize that out, and leaving 5 squared minus 1. Okay, so just working that through, we got 2 to the power of 3n plus 1 times 7. That's 1, 7. And 3 times 5 to the power of 2n plus 1 times that is 24. Now we'll look at this. This is not obviously divisible by 17. Some of these simpler ones basically will actually be able to see that we can factorize 17 or whatever, whatever property we want out of this. Can't obviously do that. So the trick here, which you see quite a lot with these, is that if we can take out what we have assumed, all right, so that bit in brackets there is f of n, then clearly this must be divisible by 17, because this factor here is divisible by 17 by event of our assumption. And then this leaves us with, there's 24 lots there, and so we take 7 out, that leaves us with 17 lots of that. Yeah, and again, this is clearly divisible by 17 now. Okay, so basically we've got when we're looking at the difference, we've got something which is divisible by 17 there, something which is divisible by 17, so the whole of the difference must be divisible by 17. Yep. And since f of n is divisible by 17, then so must f of n plus 1. Okay. So therefore, being true for n implies that it's true for n plus 1. And since it's true for n plus 1, then it's true for all n. That's our conclusion step there. Okay, all right. So three different types of examples. There are a few other sort of variants, matrices and things like that. I'm not included in this particular set here, but hopefully you've found that helpful. And thanks for listening.